Hello everyone, I'm Jesse Mason, and in this installment of Teach Me, we're going to take a look at a classic projectile motion problem involving an angled launch from uneven ground. For this problem, we're given the initial position and velocity of the projectile, and our task is to determine the projectile's range, peak height, and velocity at some point in time along its trajectory. The first step, as always, is to draw a picture. So here's the cliff from which our projectile is launched. And here's the level ground below. We'll draw a cannon to fire the projectile and also to mark its initial position. And there's our trajectory. And we're done with the picture. Not much to this one. Yet. So what are our knowns and unknowns? To start, we're given the height of the cliff, which is to say the initial vertical displacement. And that's 100 meters. Of course, we've already implied our coordinate system, but we need to be explicit and include it on our drawing. Next, we're given the magnitude of the launch velocity, the initial speed of our projectile, 30 meters per second. We're also given the direction of the launch velocity, so we'll label the angle between the velocity vector and the horizontal as theta, and theta is equal to 20 degrees. So there are some of our knowns. There are a few more that are implied, and we'll address them shortly. The first unknown we're tasked with determining is the projectile's horizontal displacement upon impact, its range. We'll label this x. And by doing so, we've implied the location of the origin, so let's indicate that on our picture. Now it should be clear to see that our projectile's initial position along the x-axis is 0 meters. We'll label the maximum vertical displacement, that is to say our peak height, as ymax. Lastly, we're looking for the projectile's velocity 2 seconds after launch. We're going to guess that the projectile, a cannonball in this case, would be somewhere around here at that time. Accuracy with our guess is unimportant because the equations will tell us the rest of the story. So at this point in the trajectory, the instantaneous velocity looks something like this. We're after the magnitude and the direction, so we'll label the angle between the velocity and the horizontal as phi. Phi? Phi? Phi, fo, fum, whatever, it's all Greek to me. And let's not forget to jot down the given time for this part. Since we'll be looking for each component of the projectile's velocity separately, we'll break v into v sub x and v sub y. And while we're at it, let's resolve our initial velocity into its constituent x and y components as well. So here's our given launch velocity, v sub o. In the vertical direction, we have v sub o sub y, and in the horizontal, we have v sub o sub x. And here's the given launch angle theta. Since we'll eventually be writing these components in terms of v sub o and theta, we'll write their trigonometric relationship right here. Let's see, so the y component of v sub o is opposite theta, so it's equal to v sub o sine theta. And the x component of v sub o is adjacent to theta, so it's equal to v sub o cosine theta. By the way, we've got an implied known that should be listed, the acceleration due to gravity. What value should we use for g? Or more to the point, is the magnitude of g positive or negative? Well, it all depends on our coordinate system, so we need to compare the acceleration vector to our chosen coordinate system. What's the direction of the acceleration vector? Downward, of course. Since we align the positive y-axis with the upward direction, and the acceleration vector is downward, that means that the magnitude of g for this problem will be negative 9.8 meters per second squared. Okay, we're finished with identifying the knowns and unknowns. Now we're ready to move on to the next step, selecting the appropriate equations for our problem. Since we're dealing with projectiles and ignoring the effects of air resistance, the kinematic equations, namely the displacement equation and the velocity equation, are entirely sufficient to analyze the motion of our projectile. Of course, our projectile is moving through 2 dimensions, so, with a nod of appreciation to Galileo, we'll apply these equations to each direction separately. So in the x direction, starting with the displacement equation, instead of s, we have x equals 1/2 a sub x, that's the acceleration in the x direction, times t squared, plus v sub o sub x, the x component of the initial velocity, times t, plus x sub o, the initial horizontal position. Before moving on, we're going to simplify this equation. A projectile's horizontal motion is unaccelerated, so we can set a sub x to 0. We've defined v sub o sub x as v sub o cosine theta, and x sub o is 0. So the displacement equation in the x direction simplifies to x equals v sub o cosine theta t. We'll label this equation 1 and set it aside for now. Now we apply the velocity equation to the x direction, and we get v sub x equals v sub o sub x plus a sub x times t. We'll set v sub o sub x to v sub o cosine theta, and again the horizontal acceleration of a projectile is 0. So the velocity equation in the x direction simplifies to v sub x equals v sub o cosine theta. We'll label this equation 2 and set it aside. Okay, so now we'll apply the kinematic equations to the y direction. The displacement equation becomes y equals 1/2 a sub y t squared plus v sub o sub y t plus y sub o. First, a sub y, the acceleration in the y direction, is the gravitational acceleration of a projectile, so we can set that to g. And we've defined v sub o sub y, the y component of our projectile's initial velocity, as v sub o sine theta. So the displacement equation in the y direction simplifies to become y equals 1/2 gt squared plus v sub o sine theta t plus y sub o. Label that equation 3, and we're almost done. The velocity equation in the y direction is v sub y equals v sub o sub y plus a sub y times t. Again, v sub o sub y was defined as v sub o sine theta, and a sub y is just g. So our fourth and final equation is v sub y equals v sub o sine theta plus gt. These four equations now constitute what we call our toolbox. Every handyman knows you got to have the right tools for the right job. The same goes for projectile motion. Simplifying the displacement and velocity equations for each direction is selecting the right tools. And with these tools, we can determine everything we want to know about our projectile's motion and trajectory. First up, determining the projectile's horizontal displacement upon impact, i.e. its range. Where do we start? Well, equation 1 would give us the horizontal displacement, but we don't have t, the time of impact. To get t, we're going to need to use equation 3 along with a key implication. At the moment of impact, the projectile's vertical displacement is 0. Now we can solve equation 3 for time. So we'll start by writing equation 3. We'll set y to 0 and rewrite for clarity's sake. Does this equation ring any algebraic bells? Perhaps if we recall its more general form and solution. If 0 equals at squared plus bt plus c, where a, b, and c are all constants, then t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Yep, that's how I remember the quadratic formula. So our 1/2 g here will play the role of a, our v sub o sine theta will be b, and our y sub o is c. So t equals negative v sub o sine theta plus or minus the square root of quantity v sub o sine theta and quantity squared minus 4 times 1/2 g y sub o, all divided by 2 times 1/2 g. Thank you. Thank you very much. Simplifying just a few terms and then inserting our values, we find that t equals negative 3.59 seconds, or positive 5.68 seconds. The negative value is not useful for this problem. Negative time? What does it mean? So we'll lovingly discard it. Now we proceed with equation 1, write it out here, and insert the appropriate values. 30 meters per second, cosine 20 degrees, and for time we use 5.68 seconds from equation 3. And we get a horizontal displacement of 160.1 meters. All things considered, not an unreasonable range. Okay, now let's determine the maximum vertical displacement of our projectile, that is, the peak height of its trajectory. We'll use equation 3 to determine this value, but we first need to obtain the time which corresponds to this moment. To obtain the time, we need to recognize that the moment our projectile crests its trajectory, the vertical component of its velocity is 0. Using this value, along with equation 4, will give us the time at which our projectile reaches its peak height. Okay, solving equation 4 for time, we get t equals negative v sub o sine theta divided by g. Inserting our values, we find that at 1.05 seconds, our projectile levels out and begins its descent, so to speak. Now we'll insert this time into equation 3 to determine the maximum vertical displacement of our projectile. And when we assign our values to the variables, using 1.05 seconds, the time coincident with Ymax for t, we find that our projectile reaches a peak height of 105.4 meters. Not very impressive, but very reasonable given our shallow launch angle. Lastly, we'll determine the projectile's velocity 2 seconds after launch. We'll need to determine the x and y components separately, so starting with v sub x, we'll use equation 2. V sub x equals v sub o cosine theta. Using the aforementioned known values, we get 28.19 meters per second for the horizontal component. We'll use equation 4 to determine the vertical component. Inserting our known values, including the time in question, 2 seconds, we get a value of negative 9.34 meters per second for v sub y. What's up with that negative sign? That negative sign implies motion in the negative y direction, that is, downward. Now at this point we could write our solution in vector notation, where the velocity vector is equal to the magnitude of the velocity's x component times the unit vector I hat, plus the magnitude of the velocity's y component times the unit vector j hat. That would give us the solution v equals 28.19 meters per second I hat plus negative 9.34 meters per second j hat, which is fine and dandy. But let's go ahead and determine the magnitude and direction of this velocity vector. So we've got 28.19 meters per second in the x direction and 9.34 meters per second in the negative y direction. We'll recombine these components to determine the magnitude of v using Euclid's 47th proposition, better known as Pythagoras' theorem. The square of the hypotenuse is equal to the sum of the squares of the legs. Taking the square root of both sides and inserting our values, and dropping the plus or minus sign, we get a magnitude of 29.70 meters per second. Physically reasonable? Check. Are we done? Not yet. We still need the direction of its motion, that is to say the angle between the velocity vector and the horizontal. To get phi, we use trigonometry. So the tangent of phi equals opposite, 9.34 meters per second, over adjacent, 28.19 meters per second. Take an inverse tangent, and we get a value of 18.3 degrees for phi. So 2 seconds after launch, our projectile is moving at 29.70 meters per second at 18.3 degrees below the horizontal. I'm Jesse Mason. I hope you found this video helpful and that I've convinced you of the utility, nay, the necessity, of creating a toolbox to solve projectile motion problems. If you have any suggestions for future Teach Me videos or just want to say hello from your part of the world, please do so in the comment section below. And as always, happy learning.